let's talk some magnetism here. So I'm gonna pull out some stuff about that I used from my stuff back in the day before. I like my stuff a little bit better than their notes. So let's go ahead. Where is magnetism? Come on, come on, come on, come on, come on. Come on. Is it really in? Oh, that's right. I usually use an IPS. No, I mean this stuff works still pretty darn well. Notes. Magnetism. Here we go. Yeah. They've got a test next hour. Yeah.
We haven't been turning in correct test corrections as long as we've been doing them, correct? Maybe as long as we do test corrections.
Wait, no, you're trying.
Oh,
yeah, you guys. What's up?
Is what I did wrong because it's secretly just adding the other two together.
That's what I was trying to figure out, but technically no, because you combine the third loop in there, and I'm doing the math, and it should work. So let me look at it a little bit later. Okay, I'm gonna check that problem specifically. All right, let's talk magnetism. Let's begin at the beginning, which sort of I suppose is a dumb sentence. Number one, we found that certain rocks, when you hold them and suspend them in the air, okay, always point north. They're called lodestones. Guess what we decided to call that side of the magnet?
North.
Called it north. Correct. So the side of the rock that points north, we called north. Here's the problem with that. Basic magnetism, which you should all pretty much know, works very, very similar to electric stuff, but not quite the same. Basically, in electric stuff, you've got positive and negative. In magnetic stuff, you have north and south. Okay? What do two north ends of a magnet do to each other? What do opposites do? Attract. What do, yeah, and so two norths will repel, two souths will repel, and two opposites will attract. So, what they had not considered, they did not know that at the time. They didn't know the interaction between individual magnets because they only usually had one single rock, okay, that would do this one thing, and it pointed north, so they called it north. But the reason why it points north, and we'll talk about this in greater detail later on, is that Earth acts like a magnet. So, if Earth is a big magnet, and the north side of the magnet attracts north, yeah, that means that actually, so now we have to separate between geographic north, which is still north, don't need to worry about that, and what is now considered magnetic north. Okay, so what is actually happening inside a compass is nothing more than a magnet itself. Okay, a compass is a tiny little magnet, and so why does it point north? Because north and south attract. That's simply all that's going on in that particular case. So if you have a tiny magnet here, and actually interestingly enough, so where's the south magnetic pole? Because of what we just said, up top in the north, it is not actually at the poles. You can kind of see from my wonderful globe right here that this used to be, so the reason there's a hole through this is this used to have a bar magnet sitting in it, so you could put a compass on this globe and it would point the correct direction, so you could kind of just play around with that type of thing, except it fell out a long time ago, so I just used it still as reference. So here we go. What you're noticing here is that this guy right here is where the south magnetic pole is. It is not at the actual pole, it is in northern Canada. And we'll talk why about this later on, but it's moving. It's always moving. Pretty much moving regularly throughout. So, where's the north magnetic pole then? In Antarctica, yes. And it is not also directly at the south pole. So, they are slightly moving. Which means, by the by, we're actually lined up really nicely since it's in Canada. For the most part, compasses here in America do in fact point north. But if I come over here to Europe, do compasses actually point north? No. Which way do they point? Northwest. And if you were standing at the North Pole, Weirdly enough, compasses point south.
There's nowhere else they could.
Yeah. And here's what's going to get really messy in the magnetic chapter. Okay? You've heard my joke before about F magnetism. You're going to see why right now. Let's say you're standing directly in Canada, right where the south magnetic pole is. Which way should your compass point?
Everywhere.
Assuming that it's three-dimensional. Down.
Where's it going?
Yeah. So the hard thing about magnetism in this particular
Wait a
chapter is
second.
you require. I'll get to it. I promise. I'll back this up. I'll talk about that later. It requires 100% requires three-dimensional looking at space and which way it's going. So first thing I really want to address in here, okay, is it hits somebody every year. Hopefully not all of you. Hopefully every single one of you in here hears me what I'm about to say and goes, duh, Spainhour. Okay. But let's just make sure. North and up are not the same thing. Okay?
What?
Okay? North and up, not the same thing. Best guess in here. Discuss quickly in your group which way is north. Discuss with Aiden. He's by himself too.
It's one of the corners of the room.
Because I've referenced it before?
I'm
Or because you remember? Because you did it.
No, I just checked in my room.
Oh, really?
Before. Wait a second.
Your room's not this room.
Wait.
I've checked in my room, and my room must. Do you live here,
Wait.
Jaden? When I'm not looking, do you come back in and go to
Somebody
sleep?
I basically did. I'm always here. Wait, I live.
Can I make a
Yeah,
suggestion
I'm
to
calling
you
that.
guys who have been
That
regularly in here in the morning, and then where does the sun rise?
West?
I don't know.
I don't know.
Rise in the east.
Rise in the east, sets in the west. Yes.
I don't know what direction.
I don't know which is. Oh, I was right.
Yeah, I don't like that you were right. Okay. Now, humor me because again, this is gonna get really messy with people later on. Which way's up? All right. So there you go. There's up. All right. Everybody's usually good with up. Okay. Hopefully you are good with up. But I know maps have messed up some people, and this hits somebody again early on, not usually later on, but early on in the chapter, it usually hits somebody like, well, it says up, but it also says later that it's going north. Like, okay, those are not all right. Maps have screwed you up. All right. So we talked about this already. Why are poles named the way they are? It actually makes perfect sense why they named them this way, even if it is dumb for ourselves right now. Okay. The reason why they named it this way is the first rocks they found that were magnetic pointed north. And so they called those north facing, and thus that became the north part of the magnet, right? Even though that accidentally made the earth flip its sides. So keep in mind that the words north and south in this case could have been anything. They could have named one side of the magnet Tom and the other side Jerry, for all we care, and then Tom would be repelled by Tom and attracted to Jerry, and Jerry's would repel, and it wouldn't matter. They could have named it anything. So it's a little unfortunate that they decided to call it north and south, because that does cause some confusion as far as the directions are concerned. But again, the best way to think about it is north magnetic and north geographic are homophones, right? Same word, different meaning. Okay, north and north. They are north, but yes, they do not mean the same thing. What does north geographic mean? What it always has. What does north magnetic mean? It means a side of the magnet that will repel another north side and attract a south side. How are we doing? Let's move on.
This diagram.
We'll get to the diagram later. It's sucky.
Okay.
It's
I was,
also-
like, looking
It's
at
also
it.
wrong.
Yeah,
All right.
Like, isn't it like?
Yeah.
It
All right.
opposite or something, yeah.
So, magnetic poles. The magnetic pole is the area of the magnet where a magnetic force appears to be the strongest. Simply put, a magnetic pole. If you look at my magnet right here, this side and this side. The poles are the either side. This next thing, if you ever watched, I'm not a huge fan, but if you ever watched The Big Bang Theory, they were attempting in, I think, the end of season 1 when they went to Antarctica to find monopoles, okay, to find theoretical ideas of monopoles. But they do not currently exist in our understanding. Every magnet has two poles. always, 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 always. Now, you might say, okay, Spinner, I got you. I'm gonna take your magnet. I'm gonna karate chop this beast. Real hard. Well, I'll give you a hint what happens. This is south, and this is north. You can kind of think of this entire bar as a gradient therein, right? A gradient from south to north. So this side might be south relative to the north, but relative to the south, it's a... So, chop this in half, that part would become north, that part would become south. Every magnet has 2 poles. Does that make sense? If that bothers you a little bit, here's been my best analogy for why it kind of makes sense a little bit. All human beings have a front side and a back side. Now, it gets really gruesome when you want to like split up human beings and that type of thing, but technically it would still be true. Cut a human being in half and there'd still be a front side and a back side, they'd just be less human and a lot more icky and gooey. All right, sorry, this is getting bad quick. All right, number 3, magnets exert a magnetic force on each other. Likes repel, opposites attract. Now, what's really going to mess with you a little bit later on when we talk about this is it is not actually the poles themselves that are interacting, but the magnetic fields that are interacting. And yes, I just said magnetic field, directly like electric fields, and you've heard my whole spiel on this before. We'll get to it a little bit later on. Magnetic fields are the best way to describe magnets. They just do icky things. Just things that don't make sense. And you go, Spainhour, how do we know? We measured it, we looked, and it does the crappy thing. You go, why? I don't know, it doesn't. All right, let's move on. Some magnets can be made into permanent magnets. Magnets that magnetize quickly are iron. Materials that do not magnetize quickly, cobalt and nickel. So here's the deal. There are only 3 materials that can become magnetic. Most students coming into this class, based on usually early cartoons, believe that magnets work with metals. That's not true. It only works with 3 very specific metals, and that is iron, cobalt, and nickel. The reason people falsely believe that all metals are attracted to magnets is the fact that what of those 3 metals do we regularly use the most of? Iron. If you hear the word steel, that is just a mixture, that is an amalgamation of iron and something else. Okay, so iron is in almost all things. So the way you can check very easily is you can take a magnet. I'll take this. Oh crap! All right, so we're gonna do the big boy. Okay, so solid amount of magnetism in this. Please do not mess around with these. Do not mess with them at all if I am not around, or even if I am around, please make sure you're asked. Okay, so I can take this big guy, and I can take a staple. Sorry, a paperclip. Okay, this paperclip right here, is it currently a magnet? No, but if you take a piece of that material and put it in a magnetic field, it is now. Okay, it is now a magnet. If this is the north side, what happens is this magnetic field flows through this paperclip and basically turns it into its own magnet. If this is north, basically it pushes through here. This is now south, this is north, and what do south and north do? Attract. What happens if I turn the paperclip around? Well, it doesn't really matter because it's still going to put the same side of the magnet on the same side relative to itself. So here we go. And actually you can see that it makes it a magnet because if I take another paperclip and I don't even hit this, and I hit this guy, you can see that the paperclip I already put on there is making the new paperclip into a magnet. And so on and so forth. I should be able to go down the line. And as this is pretty strong, if I'm very careful, it lasts for a little while. It is still a magnet right here. I give it any sort of jostle. And nope, it's not a magnet anymore. It's not going to work. Yes, sir.
Does a bigger magnet like lose strength when it magnetizes objects?
Yes, technically yes. Relatively speaking, not much, but yes, it does. The main thing that messes with magnet size is actually knocking into them physically, which we'll discuss why that is a little bit later on. But to prove to you that that is only certain metals that do this, you can see that this thing is ridiculously powerful, and yet shoot, it's one-handed. Nope, not next to computers, please. Please do not bring magnets next to your computer. It's not a safe thing. I was trying to get you guys to see this. Why won't it attract to it? You had to guess what's the door handle. It's a light metal. Aluminum. It's made of aluminum. Aluminum is not one of the three metals and therefore does not attract. Does not attract with magnets. I'm putting this thing away. I'm not holding it next to it. I should get out something that's a little bit faster. Where we go?
Mystery Spain Hour.
Here we go. Alright, these are pretty good.
Why
Alright.
is it only those three?
What's that now?
Why is it only those three?
I knew it.
I mean, there's something of a conversation there that I can get into, but A, it's kind of a little bit beyond me, and B, I would argue that we're bordering on we don't know. I think there's theories and that type of thing. I mean, that's true of a lot of stuff at this particular level as well, but could just be beyond me. Could 100% you could get to college and ask your professors like, oh yeah, that's easy, and they'll tell you. But I don't think that's necessarily the case. All right, so like it says, magnetic materials align along magnetic fields and become magnets themselves. Okay, magnets, things like the paperclip that you saw. The moment they get out of the paperclip, they get out of the field. They don't really have that continuation, and therefore they just kind of go back to being normal, which we'll talk more about what that looks like later on. Adding to this is just getting kind of the basics out of the way first. All right. So how do permanent magnets get created? Well, you could probably imagine that metal is easier manipulated when it is liquid, although that's not very easy to do, right? So how on earth would permanent magnets be created without our help naturally? Well, technically, are we all sitting in an electric field right now? That's right, a magnetic field right now. Yes, created by the Earth. Earth is a magnet that acts like a giant magnet and creates a magnetic field. Okay, so I just need a material sitting in that field. It's also not a very strong one, which you know, because is the Earth's magnetic field currently making this into a magnet? No, because it doesn't attract other paper. But, excuse me, where would it get, what would happen that it would have, say, I don't know, liquid metal around that would be sitting in the Earth's magnetic field? That, even more on the surface. Volcanoes. Around volcanoes, you will then see basically iron that is softening, okay, and then hardening in Earth's magnetic field, and thus that iron that's around there is magnetic. Broken off, it then of course becomes what's known as a lodestone, a naturally occurring magnetic rock, which if you took pieces off and broke chips off and that type of thing down to the small enough piece, this is where some very early compasses were created from. Questions?
So like, if you just like take like a regular iron rod, say like a screwdriver, and you heat it up and let it cool down.
Here's even better for you. If you've worked enough with tools, you know this. If you have a regular screwdriver and you mess around with screws a ton and you like move them and push them and move that metal a lot, they will start to attract to your screwdriver. Just two normal pieces of metal. Can confirm? There you go. 100%. Yeah. We'll talk about specifically why that is, how that's being manipulated, and that type of thing a little bit later on. It also helps that a lot of times people, specifically people in like shops and that type of things, purposely try to put their screwdrivers and stuff on magnets and sit there so they become more magnetic over time. But to your particular question, Keezer, yes, if I were to take a molten hot iron piece of metal and use a form to make it into a screwdriver, 100% it would be magnetic. That is not as great as you think it is, though. Yes.
Well, like sometimes at restaurants when you have the metal silverware, they're magnetic towards each other.
Yep.
Is that just because they were like heated up in the dishwasher or something?
I don't think they would naturally do that. I don't know. I've not heard that before, so I don't know exactly why that would be. All right. Can't remember how close we are to done here. All right. Magnetic field. So we're going to get into direction of magnetic field tomorrow. Because actually, I'm going to start this chapter with the lab rather than end it with the lab like we usually do. And it'll be kind of a little bit simpler, but this kind of gives you a good picture of what magnetic field is. So electric field is the ratio between force and charge. Okay? The electric field is the possibility of putting force onto a charge. Yes? Okay? Magnetic field is sort of the same thing. Magnetic field is the possibility of putting force on a charge that's doing something particular that we will talk more about tomorrow. So, I'll just leave it at that. Magnetic field is the region where magnetic force can be detected, and magnetic force, once again, does take place on charged particles. Compasses can track magnetic fields because, as I mentioned before, the reason they attract magnetic fields is a compass is a magnet. It's just a very tiny magnet that's sitting in there, and you can kind of think of it like a flag in the wind, right? Like its north is pointing towards south, and therefore it's straight up showing you which direction magnetic field is pointing in that particular time. Earth's magnetic field acts like a bar magnet, and we will talk about that last thing right there. You don't have to write that down because we're going to show pictures of that and kind of work on that tomorrow. Hold on a second. I just want to see what's next. I'll come back to this. I know some of you guys are still writing. Yep, I think that's tomorrow. Let me make sure I'm not missing anything. What are you doing? Yeah, I think that's pretty much it. I don't think there's anything else. No, that's it.
How do they make artificial magnets?
We'll get there. You gotta run before you can walk in.
Well, yeah, but you also have that conversation that if you heat up a really strong magnet, it becomes weaker.
So the answer to your question is where magnetic field comes from. Let's say this. Right now, as it stands right now, let's build this slowly. As it stands right now, you know there is one source currently of magnetic field, and that is a magnet. A permanent magnet, okay? But you also know correctly that we create magnets. And I can make magnetism happen in here. If you've ever heard of an electromagnet, that's like when you go to with those cartoons again, you go to the junkyard and you see the big thing come down and turn on the magnet and everything goes up and it goes to a spot where it wants to turn it off. So that means we can somehow do something to turn magnetic field on and off. Which we'll discuss how to do that a little bit later on. But right now, your source of magnetic field is other magnets. Yes.
Why isn't all iron magnet? Like,
We will discuss that as well.
Wouldn't it like have to be liquid at one point? To be
Back in the day, you said.
if formed
Yep.
on Earth.
Yep.
There's also a
And then
magnetic
it'd be
field
wet.
that's slow, right?
I will say this. So here's a good thing to note on that particular front. So the best way that makes sense to store magnets is next to each other, right? Just in terms of my doing stuff in this class. Obviously, you put all things of the same type together so I can go get them. The problem is if I put a bunch of magnets in a thing, what's going to be the natural way they orient themselves with each other? Opposite. So that means the magnetic fields are pointing the opposite direction, which means what's happening to both of them is they're sitting in the opposite magnetic field, which is slowly over time, a lot of time, but over time it's making them weaker and weaker and weaker and weaker. So that's the start of your question. But there's something to it. All right, so that's the beginning of magnetism.